Okay, we're going to make a start. For some reason, the microphone's not working, so I guess I'm going to have to stand here. I'm not sure I can stand here for the duration of the lecture. I shall try not to wander off. Okay, so quick update. William is doing better, but he's going to be out of commission for a little bit. Again, please leave him alone. We're currently trying to figure out. I think that actually one of the GSIs from last year is going to slot in and take on his GSI role for the next month or so while he recovers a little bit. So we're still trying to work through that, figure that out. So we will let you know when we get to that point. I see that the class attendance is diminishing. Maybe I should throw an impromptu quiz into the class schedule. Maybe you could share that with your friends who are not here right now. Okay, so also the midterm, the grading of the midterm has also been slowed a little bit because of this, and I know that they are almost done with it, so hopefully come Tuesday we'll have the final the grades for the midterm, but we don't have them quite yet. My apologies for that. All right, so let's move on into the material today. This is my favourite lecture. Well, actually, that's not quite true. It's one of my favourite lectures. My favourite lecture comes in the last third of the class, but you'll see why. We're going to talk about wiggles, and so we're going to sort of migrate. We've been talking about the process of building up to an earthquake and faulting, and we're going to go make the transition from talking about faults to how you actually generate the wiggles, the seismograms, in earthquakes. And so, of course, it's the seismograms, it's that data that informs us about the earthquake process, and so it's those wiggles, in fact, that provide all of the information, all of the basis for pretty much all of the material that we've actually covered so far in this class. So we're sort of getting into the grips of the data. I want to illustrate, so don't forget the reading. I know that as we get into this middle third of the class, this is some of the material that some members of the class find a little more challenging, so that's even more reason to make sure you go and review the reading material. Okay, but I'm going to introduce this in the concept of the Northridge earthquake. So how many Southern Californians do we have with us? Oh, how about that? It was the Northern Californians who decided not to show up today. And how many of you felt the Northridge earthquake? So the Northridge earthquake was in 1994. How many of you were were alive in 1994? Oh no, dear oh dear. Every year it's a diminishing number. We're going to have another earthquake, otherwise I won't know what to talk about. So the Northridge earthquake, of course, is the last major event that we had in Southern California. The Napa earthquake really doesn't fall in this category. So in Northern California, we still think about Loma Prieta, and Southern California, we think about the Northridge earthquake. It was magnitude 6.7 earthquake, killed about 60 people, 1,500 people seriously injured, 12,000 structures damaged, a total cost of $15 billion. This was not a big earthquake. And you will see precisely why I say that about halfway through today's lecture. But some photos from this event. One of the sort of stories of this earthquake was the collapse of highway structures. And you can see two examples here. I guess I can stand like this. You can see two examples here. And so this is actually was the beginning of Caltrans's retrofit program to improve highway structures, and specifically the columns that hold up a lot of the overpasses in highways. And then this side, this is just an incredible picture. So let me help make sure you're understanding what you're seeing. I think, if I remember, I think this is a creek. Is that a road? I can't tell. On the bottom, actually, I think maybe it's a road. These might well be cars. So anyway, the point is that there's an overpass here, a highway overpass, and the highway. So these two sections here are the main sections of the overpass, and then the highway over here, this side of the photo is just at grade level. And what you can see here is it's the connections between the overpass and the regular highway that have actually collapsed. And so what actually occurred in this event is that these two sections started to oscillate due to the ground motion, and they obviously remained intact, but the connections between them and the sort of regular roadway collapsed on the two ends. And you can see that there are actually cars on this section. So they were going along the highway at the time of the earthquake. They started to feel the shaking. They put on the brakes and stopped and didn't drive off the ends. And if I recall correctly, nobody actually drove off the ends in this particular case. In this case, there was one fatality. It was actually a police officer. This earthquake, just like the Napa earthquake, occurred at very early in the morning, 4 a.m. as I recall. It's not written up here, but very early in the morning. So just like the Napa earthquake, there weren't many people out on the roads or in commercial buildings. And so that was one of the reasons why the impact of this earthquake was much less than we would expect if we had the same earthquake in the middle of the day. But the fatality here was a police officer who was driving along the highway, didn't know that it had collapsed and just drove off the end of the highway. Okay, so we're going to use the Northridge earthquake to talk about the relationship between faults, ruptures, and then seismograms. So a little bit of the context here. So here's a map. This is actually a geologic map of California, and in orange is the San Andreas fault. Of course, we all know that this is a right lateral fault. And what you can see is what we call the Big Bend in Southern California. Just to kind of highlight that a little bit, the fault here is pretty straight, and the fault down here is pretty straight, and then this is what we call the Big Bend. So the fault itself actually goes through a turn, and this changes the nature of the deformation that we have along this section, which is much of populated Southern California. Okay, so up here, the motion on the fault is parallel to the fault, but because of this bend here, we now have this rock mass here, this piece of crust is going in this direction, and this piece of crust is going in this direction, and of course the two collide. And so because we have that sort of collision, a oblique collision, we get mountains formed, and of course that's what the transverse ranges are all about. So another sketch just to illustrate that. So here's the Big Bend in Southern California, and because of this collision of the crust up here and the crust down here, we get mountains formed exactly the same way you get mountains formed in the Himalayas. You have these two pieces of crust pushing into one another. The difference here is that this is an oblique strike-slip fault, so it's primarily a strike-slip fault, but with a little bit of collision, and so we get these transverse ranges. And just to point out, if the San Andreas fault was instead a left lateral fault, then this block would be pulling away from this block, and we would actually have a big basin here rather than a mountain range. Okay, so it's just the inverse deformation would be occurring if the motion on the fault was in the opposite direction. Okay, so that's the sort of tectonic setting for these events, well, for earthquakes in Southern California, and including the Northridge earthquake. So here's another map that shows the main earthquakes over the course of the last few decades. This is the area that we believe ruptured in the Northridge earthquake, and then you can see it overlaps an area that ruptured in 1971, the San Fernando earthquake. I'll show you how those two relate to one another in a minute. A much smaller earthquake, 1987, the Long Beach earthquake. Okay, I show you that map first because it's easier to understand than this one. This is the one that's out of your textbook, and it shows earthquakes going back much further in time in Southern California. So again, the Northridge earthquake, this is the area of the fault plane that we think ruptured. You should be asking yourself right now, how do we know that that's the part of the fault plane that ruptured? We'll come to that. The San Fernando earthquake, and then the other one that's really important to point out, I think, is the earthquake that occurred down here, 1933. So this sausage is kind of a best guess. But the reason that this is an important earthquake is that the 1933 earthquake, what it was known for, I said that earthquakes become known for particular things. 1933 earthquake is known because it caused a lot of schools to collapse. And so following the 1933 earthquake, they introduced the Field Act, and it's the Field Act that mandates that schools have to be built to a certain standard, a higher construction standard. And it's now widely recognized that that is a critical that's critical legislation, and has reduced the number of fatalities in earthquakes ever since. So I just wanted to point that out. Okay, so to the Northridge earthquake specifically, so this is a shake map. You're now familiar with what a shake map is. It just shows the actual distribution of the shaking. The star shows the epicenter of the earthquake. This square is sort of a simplified representation of the fault plane that we think ruptured in this particular earthquake. Is it working? No? Okay, thanks. So this is just an approximation of the fault plane, but then the colour scale, of course, shows the actual shaking. And what's important to recognise here is that the shaking is sort of centred up here. So the shaking, the red patch is sort of a circle like so, centred about here, and the epicenter is down here. So the strongest shaking is offset with respect to the epicenter of this earthquake. And that is because this is a thrust fault. Okay? And so the thrust fault, of course, this is not a strike slip fault. This is not the kind of ruptures that we've been talking about up until now for most of the San Andreas. This is a thrust fault where you have these two blocks pushing into one another because of the big bend, and you have a dipping fault, and the rupture actually propagated up the fault plane, causing most of the shaking to be to the north, which is in the Santa Susana Mountains. So that is why this earthquake, even though it was a magnitude 6.7 earthquake, isn't considered to be really a particularly big one, because most of the shaking generated by this earthquake was in the Santa Susana Mountains, where very few people live, as opposed to in the San Fernando Valley. The epicenter is in the San Fernando Valley, but the shaking in the San Fernando Valley was not that strong because most of the shaking was pushed to the north. Okay? So this just shows the grayscale is the topography in a little more detail so that you can see it with the faults shown on it. So this is these are the Santa Susana Mountains. So this is a thrust system. When they say it's a thrust system, it means that there's a series of faults, but we can't identify all of the individual faults. Likewise, the Santa Susana Mountains up here, also a thrust fault zone, and then this flat region here, this is the San Fernando Valley. Okay? And so the epicenter of the Northridge earthquake was located right here at the red circle. Okay, so we have two sets of thrust faults that are responsible for these two mountain belts that are all within what we call the transverse ranges. In the bigger picture, these are all within the transverse ranges. Okay, so finally to what the actual rupture, the earthquake rupture itself looked like. So this is a very similar map. It's not quite as clear, but this here is the Santa Monica Mountains to the south and the Santa Susana Mountains to the north. And then hopefully you can just about make out this flat zone. This flat zone is the San Fernando Valley, the epicenter of the earthquake, and then this rectangle is a surface projection of the fault plane. But this is the actual fault plane, and it has a 40-degree dip. Okay, so the fault plane is dipping about 40 degrees, so like this. Okay, it's dipping in this direction, so it's dipping down to the south, essentially. Okay, so this is a thrust fault dipping to the south that we have the earthquake rupture occurring on. And so this is just a rectangle, of course. Of course, the fault that ruptured is not this perfect rectangle. That would make no sense. But this is the rectangle that we're just sort of representing, and then the colours on here show the amount of slip on the fault plane. So obviously when an earthquake occurs, these two fault planes are slipping past one another. And when I illustrate this with my hands, the whole fault plane is moved by 1 centimetre, 2 centimetres, whatever it might be. Okay, so in this, when you do it like this, we think of the rupture as being very uniform, the same amount of slip everywhere on the fault plane. But in reality, of course, the amount of slip varies. Off at some distance, of course, it's zero. So if you think about an earthquake on the San Andreas fault, which is many hundreds of kilometres long, the earthquake doesn't necessarily rupture the whole fault. So out at distance, the slip is zero. And then as you get into where the earthquake occurred, of course, the slip increases, and somewhere there's going to be the maximum amount of slip. And as you move away from the maximum amount of slip, you get less and less slip until you get zero slip. And that pattern can actually be quite complicated, as shown in this little diagram here. So the maximum slip is this purple patch up here, a total of 3.2 meters. Okay? So that means at where the maximum slip occurred, it's the equivalent of from where I'm standing to the middle of this double table. Right? That's how much the subsurface moved. Right? So 3.5 meters is about 4 rows of the seating, 4 rows of seats. Okay, so that's how much it moved in the centre. But also notice that this is what the hypercentre. The hypercentre, of course, is where the earthquake actually initiated. So the hypercentre is the place at depth beneath the epicentre. The epicentre is the place on the surface where the earthquake occurred, and of course it occurred at some depth. The hypercentre is the point in the subsurface where the earthquake initiated, and that's down here. So you can see some scale here. This is going from 5 kilometres depth to 19 kilometres depth. Okay, so this is many kilometres. This total area of this fault plane is many kilometres by many kilometres. The rupture started down here, and then it grew outwards. The rupture with time grew out from this hypercentre, and the place where most slip occurred was up here. Okay, so there's a time history here now as well. So not only is the amount of slip variable over the fault, but also there was a time progression where the slip started at one place, and it kind of gradually moves out and further and further out. All right. So this is what it looks like in time. So if we do a snapshot of the slip in the first second, this is what it looks like. So this is that same fault plane. Here's the hypercentre. And so the slip in the first second looks like this. It's less than 1 metre of slip close to the hypercentre. And then the slip in the second second has moved up the fault plane a little bit. It's moving up in this direction, closer to the surface and to the northwest, I guess. But the slip has also increased in this second. So now we have a total of about 1 to 1.5 metres of slip during this 1 second interval. Third second, fourth second, you can see the rupture gradually migrating up towards the top of the fault plane and then dying out after about 7 seconds, let's say. So the total duration of the earthquake was 7 seconds. That's how long it took from when the earthquake began to when the rupture stopped. 7 seconds. Okay? So for 7 seconds, energy was being radiated out from this fault, and the shaking that people would feel, of course, would last even longer than the 7 seconds. Yeah? Okay, so the question was, when did people start to feel the shaking? So people would start to feel the shaking when the seismic energy from this rupture reached the surface. Okay, so when this earthquake, when this earthquake started, energy starts to be radiated, and energy is being radiated from the fault plane where the rupture is occurring continuously for the duration of the event. And this energy radiates as P waves and S waves. That's what we're going to talk about in a few minutes. I'll come back to that question. Okay, any other questions about the rupture? I want to make sure everybody understands this concept. All right. Okay, so obviously what's implicit in this is that we're able to actually determine where the fault plane that ruptured is. So we can determine that the fault plane was at some depth and it had some dip and what the orientation of that dip is. And we can do all of that from the seismic data, from the wiggles that we're building up towards. And so if I now plot this fault plane in cross-section, this is a north-south cross-section across the San Fernando Valley. So this is the Santa Susana Mountains, San Fernando Valley, Santa Monica Mountains to the south. And then these are actually all of the aftershocks. So I asked the question earlier, how do we know what the fault plane looked like? There are several ways, but one of them is you just map the aftershocks. So these are smaller earthquakes that occur in the days and weeks after the main shock. And the aftershocks essentially illuminate the fault plane. So you can think of this as being, you have some rupture on the fault. Of course, this causes all kinds of turmoil within the crust. And then the aftershocks are kind of the rock that has moved sort of settling itself down into a comfortable position. And so as it does that, it has all these little aftershocks that radiate energy. So you can essentially use the location of aftershocks to tell you about the orientation of the fault plane. Okay? In fact, that's how the orientation of this fault plane was determined. And so this is a cross-section. These sort of pinkish, reddish dots are the aftershocks for the Northridge earthquake. And so the Northridge earthquake was on this fault plane that had a dip to the south. And what's kind of interesting about this is that these are the aftershocks from the 1971 San Fernando earthquake, and it has a fault plane that's dipping to the north. So what we actually have in this environment is these thrust planes that are crossing one another. So as you have compression from the north and south direction, so you have compression, that compression is being accommodated by motion on these faults. Of course, it doesn't matter whether the dip's in this direction or this direction, you can accommodate that motion. All right? So we're getting it from both places. Now, in both cases, these were blind thrusts. What that means is that there was no obvious surface fault break. So when people go and map where the faults are in California, there was no Northridge thrust fault. So when this earthquake occurred, it was a big surprise. People didn't know that this fault was there. That was one of the big lessons of the Northridge earthquake, is that it's very unlikely, well, we know that we do not know the location of all of the faults that are distributed throughout Southern California, throughout the transverse ranges, and the Northridge thrust fault is one example of that. I'm sure I've said this before, but just in case I haven't, even despite all of the instrumentation we have in California and all of the effort that's been put in, we still have not had an earthquake that was not a surprise in some way. Okay? So we still don't understand where all of the faults are and the nature of all of the earthquakes that we need to understand, and that's why instead we have to take this very broad view when it comes to earthquake hazard, of averaging out over broader areas when it comes to mitigating earthquakes. And we'll talk about that in the final third of the class. Okay, so to recap here, this is just another schematic that shows the relationship between the fault plane, this calls it the focus, the hypercenter of the focus, it's the same thing, and then the rupture. So we have a fault plane, dipping fault plane here. The earthquake initiates at the hypercenter, or the focus, and the rupture then grows out from that hypercenter, and the amount of slip can vary in this region where the rupture has occurred. Okay? So that's the relationship between the fault plane, which has a dip and a strike, the earthquake focus, and then the epicenter, of course, is on the surface, directly above the focus or directly above the hypercenter. And then the rupture itself is the portion of the fault plane that actually slipped in an earthquake. Okay? I'm going to just use these terms without thinking about it, so I want to make sure everybody's clear on what I mean. Any questions about these and the relationship between them? Excellent. Okay, just another diagram. So we have our fault and we have our rupture, but this is now showing the energy radiating from the fault. So at every point on the fault where there's any amount of slip, energy is radiated throughout the Earth's crust, P waves and S waves. And of course, it's that energy that we then feel at the surface in terms of shaking at the surface. It's that energy that which causes the damage. There are two types of energy that radiates out: P waves and S waves. Okay, and so these P waves and S waves, they leave the fault at exactly the same moment of time. Right, the energy is created by the rupture on the fault, but they travel through the Earth's crust through two different mechanisms that we're going to talk about, and that means they travel at two different speeds. So they arrive at the surface at different times. So the P arrival and the S arrival, they reach the surface at different times, but they left the fault at exactly the same time. And then the third type of wave that we will talk about is surface waves. Surface waves are actually just a combination of lots of S waves that are bouncing around inside the Earth's crust. They take longer to arrive because the energy has to be bouncing around. But surface waves are the waves that are typically largest. Certainly when you look at teleseismic arrivals, surface waves are largest and they come latest. So when you look at a seismogram, and we're going to look at a bunch over the next week or so, you'll typically see a P wave arrival first, an S wave arrival followed by a surface wave arrival. Okay? All right, so let's look at one of these fault ruptures. I just want to introduce you to the Hayward fault again. Just to remind you, we've talked a lot about the Hayward fault. So the Hayward fault, of course, runs through the East Bay. So here it is on a map. So when you look on a map, of course, it's just a line. But if we now cut down into the Earth along the Hayward fault, we can look at a picture of what the fault plane itself looks like. And this is the one that we've looked at. This shows the amount of slip, or the degree to which it's locked versus creeping through the East Bay, San Pablo Bay, Richmond, Berkeley, Oakland. Okay, remember this is that locked patch beneath Oakland. What's a possible source of an epicenter of an earthquake in the future. Okay, so this is our picture of the surface. So it's like we've cut down into the Earth and we're looking at the fault plane sideways. I just want to orient you. So we're going to take exactly the same view now with this one. So here's the Hayward fault again. This is the surface. This is at 18 kilometers depth. And so we're looking at it sideways on. So this is the south and this is the north. Okay, and what I'm actually going to show you is a simulation of an earthquake rupture propagating across this fault plane. Okay. So you saw that it began, coincidentally, right where I clicked. And this is the rupture itself propagating out. What's been left behind, this colour here indicates the total amount of slip, and then this sort of fire colour scheme shows the slip rate. So this colour scheme is showing where the earthquake is actually rupturing the fault at a given point in time, and then this is kind of the total amount of slip that occurred at a point. So after the fault, we have a picture, after the earthquake, we have a picture that looks like this, and shows the amount of slip that occurred on the fault plane. So this is similar to that one that we looked at for Northridge earthquake, okay, where we saw 3.2 meters of slip. The amount of slip in this simulation goes up to 3 meters. And I didn't say, sorry, this is a simulation for a magnitude 7 earthquake on the Hayward fault. Okay, this is a simulation, this is a computer model. This is not a real earthquake, but obviously a lot of seismologists work very hard to try and understand the rupture process, and one way of doing that is to then simulate ruptures and see how they compare to observations of ruptures. So this is some work done by Brad Agar at the US Geologic Survey. And so this is a simulation. He has a whole bunch of them. I've chosen this one because it's a magnitude 7 on the Hayward fault. It's the earthquake that you should all be most concerned about, at least while you're at Berkeley. So this shows the distribution of slip. You saw the earthquake started, I think, somewhere up here. You can see that there are patches of high slip like here, and then patches of low slip, and then high slip. You can see that the area that slipped varies along the fault. So this patch up here didn't slip at all, but this patch at depth did slip. So this gives you a sense of the complexity of the rupture. Let me play it again. So it began at the hypercenter. This is the rupture front propagating out to the north and to the south. You can see the slip rate. It gets very high at the rupture front as it's propagating out, and then it gradually dies away as in the slip stops on the fault plane, and again we're left with the rupture. Okay, questions? Yeah?
The area where it's locked, that was locked.
So you mean like here? So this area here actually there was slip, because if there had been absolutely no slip here, then the earthquake would have stopped. Okay, so this piece specifically where I'm pointing now, it looks dark, it is dark, meaning there was very little slip, but there was some, otherwise the earthquake would have stopped. This stuff down here didn't slip at all. And your question is that a locked section? So there's a difference between this previous figure. This is looking at the creep rate on the fault. Okay? So this is looking at creep on the fault over a long period of time. And so when we look at creep on the fault, we see creep is going on over here, but there's no creep going on right here. This is the locked patch. And so that's different to the question of creep